Today on Macaulay Math, the fundamental theorem of algebra, intro. Okay, good day. I'm Professor Macaulay. This is Math 150, Pre-Calculus, Lesson 8 on the fundamental theorem of algebra. Our goals for today. We're going to use the fundamental theorem of algebra to determine the number of zeros of polynomial functions. We're going to find the zeros of a polynomial function, including its complex zeros. We're going to find conjugate pairs of complex zeros. We're going to find the zeros of polynomials by factoring. And then finally, we're going to solve polynomial inequalities. You may ask yourself, why did we need to go all the way to lesson 8 of pre-calculus before we got to the fundamental theorem of algebra? But the answer to that has several implications. The fundamental theorem of algebra states that any polynomial function has zeros, but those zeros can be real or complex numbers, and those zeros affect the factorization of a polynomial differently. So while the theorem is fundamental to algebra, its implications and uses are anything but fundamental. The fundamental theorem of algebra. If f of x is a polynomial function of degree n, where n is greater than 0, f has at least one zero in the complex number system. This essentially says that no matter what type of polynomial you have, it must have a zero. That zero can be either real or it can be imaginary. A result of the fundamental theorem of algebra is the linear factorization theorem that says if f of x is a polynomial of degree n, where n is greater than 0, then f has precisely n linear factors, and that can be rewritten as f of x and then a product of linear factors with a possible coefficient out front. And we'll have an example about this later on, where all of these are complex numbers. Now, in the past, we've talked about factoring polynomials, and those factors usually end up having either integers or fractional values in them. The linear factorization theorem says that you can write as a product of factors with even more values than that, which could include irrational numbers like the square root of 2 or complex numbers like 3 plus 4i. Those are all possible values that you could put in for c in each of these spots, and we'll talk about an example about that later. There are some additional things that we need to consider from that. A polynomial with real coefficients can be written as the product of linear and quadratic factors with real coefficients, where the quadratic factors have no real zeros. This type of factorization is said to be irreducible over the real numbers. And so even though in this last statement we said that everything can have precisely n factors, if some of those factors are imaginary, then we could end up with a quadratic factor that is irreducible over the real numbers because its zeros are in fact imaginary. Complex zeros always come in conjugate pairs if the original polynomial has real coefficients. So if you were given a polynomial where all of the coefficients are real numbers, and you know that one of the zeros is a complex zero, then its conjugate must also appear in that list of linear factors. And we'll have an example of that. Conjugate pairs of complex numbers, we talked about this in the last lesson. If a plus bi is a complex number, then its conjugate is a minus bi. And we already see that in the quadratic formula. If you recall, quadratic formula states this: if ax squared plus bx plus c is equal to 0, then x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And so essentially what this says is that if a, b, and c are real numbers, and you plug this into here, and what's underneath the radical turns into an imaginary number, you will have complex conjugate. Here's your positive, here's your negative. First example says, given this function, write it as a product of linear factors, and then verify with graphing calculator if possible. Not sure it's going to be possible for this one, but we'll see. So I start with f of x is equal to x to the fourth plus 29x squared plus 100. And I look at this thing, and this is of quadratic form. And I look at this thing, and I see that it has 1, 2, 3 terms. The final term is a constant, and the degree of the second term is half the degree of the first term. So I know that it's in quadratic form, so I'm going to try and factor it. And I ask myself, what are two factors of 100 that add up to 29? Well, that's not too difficult. 25 times 4 is 100, and 25 plus 4 is 29. So this becomes the factorization x squared plus 4 and x squared plus 25. Now, these are two quadratic factors. And we will see that they are irreducible over the real numbers. If they say factor completely over the real numbers, I would be done here. But again, we are going to take each of these and extract square roots. So I will set each of those equal to 0. X squared plus 4 equals to 0. X squared plus 25 equals to 0. And we will subtract from both sides. So I'll have x squared equals negative 4 and x squared equals negative 25. And again, take square roots. And I can't stress enough, because students miss this all the time, we have to add plus or minus every time we take a square root. So I'll have x equals plus or minus the square root of negative 4, and x equals plus or minus the square root of negative 25. So here we'll simplify, and remember, we'll say that this is plus or minus the square root of 4 times negative 1, and this one is equal to plus or minus 25 times negative 1. The square root of 4 is 2, and the square root of negative 1 is I. The square root of 25 is 5, and the square root of negative 1 is also I. And so these are the zeros. It says up here, it says write as a product of linear factors. So even though we know the zeros, and we know that zeros and factors are related, this does show that we have our complex conjugates for each zero. So if I have 2i, its complex number would be 0 plus 2i. Its conjugate is 0 minus 2i. And the same thing with 0 plus 5i and 0 minus 5i. But the product of linear factors, we could say that f of x, we're going to make factors out of each of these, and we'll have x minus 2i, we'll have x plus 2i, we'll have x minus 5i, and we'll have x plus 5i. And again, this meets the fundamental theorem of algebra. It was a polynomial. It has at least one zero in the complex numbers, and since it was a polynomial of degree 4, we have 4 linear factors, and all of them were pure imaginary numbers. 1, 2, 3, 4. Part B says to verify this with a graphing calculator if possible. And so let's go to Desmos and take a look at this. We do know that there are no real zeros, so it won't cross the x-axis. But we can at least look to see what the results of that might be. If I type this into Desmos and we can see it, there's nothing in this graph, but we do know that it's a fourth degree polynomial, so its end behavior is up to the left and up to the right, and it has a y-intercept of 100, so we can't see that in this particular window. So let's go and hit our graph settings and go to the y-axis and use that powers of 10 method to at least try and see what we want to see. So start with a 1, I'll add a 0, I'll add another 0, and we know we had the bottom there. And so there is our graph. Not a whole lot going on there. And clearly it doesn't cross the x-axis anywhere, and we know that it wasn't going to because all of the zeros were imaginary. Next example says write a polynomial with real coefficients that has zeros. So this particular example is doing the opposite of the last example, where in the last example we started with a polynomial expression and we found zeros and factors. Here we're given zeros and we need to write a polynomial. And so we will start by writing factors. And so we'll start with x plus 3, x plus 3, and x minus I. Now we have written a factor for each of these three zeros. When I plug in -3 here, I'll get 0. When I plug in I here, I'll get 0. So these are the correct factors. But they say in the beginning that we need to have real coefficients. And for us to have real coefficients, we learned up here that if you have a complex 0, you need a conjugate pair so that the polynomial has all real coefficients. So we need to add x plus I. We're adding x plus I. So we're adding so that it has real coefficients. All right, so we're going to multiply. And we'll multiply these two together and these two together. And so for the first one we can distribute. We can go x times x is x squared. X times 3 is 3x. And then 3 times x is another 3x, giving us a total of 6x. And then 3 times 3 is 9. And then for this second one, you will recall that a plus b times a minus b is a squared minus b squared. Alright, so if I do that, I'll get x squared minus I squared. Well, I squared is -1, so this thing simplifies down to x squared plus 6x plus 9. And then I have x squared plus 1. So here I will distribute. And so x times x is x to the 4th. 6x times x squared is 6x to the 3rd. 9 times x squared is 9x squared. X squared times 1 is just x squared. 6x times 1 is just 6x. And then 9 times 1 is just 9. And then I'll add, and I'll say my final polynomial here is x to the 4th plus 6x to the 3rd plus 10x squared plus 6x plus 9. And I have written a polynomial that has all of those zeros. Next example, it says find a polynomial of degree 4 with real coefficients that has the following zeros, 1, 2, and I, and has a function value of, when you plug in 1 for f, you get 8 out. Alright, so this is a similar problem to the last one. We do know that we have 3 zeros that are given. They want degree 4, so we know that we're going to have at least one more 0, and that 0 will be the conjugate of this I right here. So we will set up our linear factors. And we will set them up. We'll go, the first one is x plus 1, and then we'll have x minus 2, and then we'll have x minus I, and then we'll have x plus I. Again, we will multiply. Multiply these two together. We'll multiply these two together. X times x is x squared. X times negative 2 is negative 2x. 1 times x is positive x. Plus the negative 2x will have negative x. And then 1 times negative 2 is negative 2. And then because these are conjugate pairs, we can say that this is going to be x squared minus I squared. And remember that I squared is negative 1. So I got x squared plus 1. Because minus negative 1 is plus 1. And here we will distribute again. And go x squared times x is x to the 4th. X times x squared is negative x to the 3rd. And then negative 2 times negative 2 times x squared is negative 2x squared. 1 times x squared is x squared. 1 times negative x is negative x. And then 1 times negative 2. 1 times negative 2. 1 times negative 2 is negative 2. We will add everything together. X to the 4th minus x to the 3rd minus x squared minus x minus 2. And so this is the function that we think we want. And if we go over to Desmos and type that in, we see that it has the real zeros at x equals negative 1 and a 0 at x equals positive 2. And since it only crosses the x-axis at 2 places and is a 4th degree polynomial, we know that it has to have 2 imaginary zeros that are conjugates of each other, which is what we have right there. The only thing that we don't know yet is when I plug in 1, will I get 8 out? Well, let's go and check in Desmos. So if I go f of 1, I get negative 4. Well, I need something other than negative 4. All right, I need it to be positive 8. So I ask myself, what times negative 4 is positive 8? Well, if I multiply by negative 2, I'll get positive 8. So to make this easy on myself, my final answer here, I'm going to multiply this thing by negative 2 and we'll just distribute. And I'll say f of x is equal to negative 2x to the 4th plus 2x to the 3rd plus 2x squared plus 2x plus 4. And we will type that into Desmos. And so here we have that function in there. And since we didn't add any zeros, it has the same zeros as our original. And when I plug in 1, I do get, in fact, 8. So it has the same zeros. I have the correct value at 1. This is my correct final answer. Solving a polynomial inequality. Write the polynomial in standard form with all terms on one side of the inequality. Find the zeros of the polynomial. These are called our critical values. Then use critical values to make a sign chart. You can also use a graphic calculator, and I'll show you how to do that. Do a sign analysis, positive or negative, over the intervals of the sign chart, and then use the sign analysis to determine which intervals make the inequality a true statement. So let's do an example of that. Let's go through it. It says solve this polynomial inequality. I have that here. First step says write the polynomial in standard form with all terms on one side of the inequality. And I have done that here. And then it asks us to find the zeros. These are going to be our critical values. So I'm going to factor this, and because I've got 4 terms and I notice that these 2 are positive and these 2 are negative, I am going to attempt to factor by grouping. And if that doesn't work, we'll have to go and do the P over Q method. But if I group these first 2, go x to the 3rd plus 2x squared, and then I go minus. Now I'm going to put that minus out there, and when I group here, because I'm now distributing that negative, it's going to be 9x and then plus 18, still greater than 0. And then I'll do a GCF, greatest common factor of each group. So we'll go x squared, and then I'll get x plus 2, and then I can factor out a 9 from both of these two, so I'll have 9, and I'll have x plus 2. And it's at this point that I feel confident that what we're doing is correct. This is the correct method, factoring by grouping, because what's in this set of parentheses and what's in this set of parentheses are the same. I'm going to factor out an x plus 2, so I'll have x plus 2x squared minus 9. And I have a difference of squares. And so a squared minus b squared factors into a minus b and a plus b. And so my final factorization is x plus 2, and I'll have x minus 3, x plus 3, and we want to know where that is greater than 0. Alright, so I have found the zeros. These are our critical values, and then I want to use these critical values to make a sign chart. Okay, so let's go down here. There's my line, and I have, let's see here, the smallest one will be at -3, then I'll have another one at -2, and then I'll have one over here at +3. Those are my zeros. And so I want to pick a value in each of these intervals and determine whether it's positive or negative. And why positive or negative? Well, if it's greater than 0, it's positive. If it would be less than 0, it will be negative. Alright, so if I pick, say, -10, -10 makes that negative. -10 makes this negative. -10 makes this negative. Negative times a negative is a negative. I need -2.5, somewhere in between these two. -2.5 makes this negative. -2.5 makes this negative. -2.5 makes this positive. I have 2 negatives and a positive. This is positive. Alright, between -2 and -3 is 0. So I'm going to choose 0. That'll make my life easy. 0 makes this positive. 0 makes this negative. 0 makes this positive. Positive times a negative times a positive is a negative. And then if I pick, say, 10 in this interval, 10 makes that positive, 10 makes that positive, 10 makes that positive. This is positive. Alright, so we want to know what values for x makes this expression greater than 0. Well, it's greater than 0 on this interval, and it's greater than 0 on this interval. So my final answer is going to be, using interval notation, -3 to -2 union with 3 to infinity. Now, we can use graphing calculator to help us do that. Let's type in the original function. So here is the original function, and we can see that we did find the correct zeros, but this is a function and this is an inequality. This is asking us to find the x values
where this graph is greater than 0. So when I look at this graph, it's greater than 0 here, and it's greater than 0 here. So between -3 and 2, it's greater than 0. And from 3 to positive infinity, it's greater than 0. I am very confident that this is our correct answer. Well, that's all I have for today, folks. So, Star Wars fun fact of the day. During the filming of the Endor scenes in Return of the Jedi, Peter Mayhew, who played Chewbacca, was instructed not to wander off because there is a real fear that he may be mistook for Bigfoot and shot. So don't walk around the forests of Northern California in a Bigfoot costume. They may shoot you. That's all I got. Have a good day. Goodbye.